Hey everybody! Today we are going to look at how to find the slope of a linear function from a data table. So you can see two data tables. One simply gives me x and y values, and then in a minute we'll look at this data table where we have two variables in the real world. But let's start right here. I have x values, I have y values, and we understand that these are ordered pairs on a graph. 0, 3 is an ordered pair. 2, 11 is an ordered pair, and so on. So if I think of slope as the change in y divided by the change in x, then when I create a mathematical calculation, I need to put a change in y on top divided by a change in x. Let's see what that looks like. For me to go from 3 to 11, that's a change of positive 8. Okay. For me to go from 11 to 19, that's a change of positive 8. And if we know it's a linear function, we should see the same pattern every time. That's a change of positive 8. And from 27 to 35, that's a change of positive 8. So for a linear function, what I'm seeing here is when these intervals over here are the same, then I'm seeing a common first difference. That's my common first difference. Because here I'm going plus 2, plus 2, plus 2, plus 2 every time. So I have those same intervals, and this is going up constantly. As x goes up, y is also going up. So that we know the slope is going to be positive. And if I want to do that calculation, my slope represented by m is change in y, which we already said was 8, divided by change in x, which was 2. So we have a ratio of 8 over 2, 8 over 2. So the rise over run, 8 over 2, gives us a slope of 4. And if I look at this on a graph, just adjust here, okay? As you can see, I have y equals 4x plus 3. That is the linear equation for that function, which we can talk about at a different time. But here I have a y-intercept of 3, and since my slope is 4, I should be able to see a change in y. Here's the y-axis, 1, 2, 3, 4 over 1. So positive 4, 1, 2, 3, 4, positive 1, moving up and to the right. 1, 2, 3, 4, positive 1. Or I can go 1, 2, 3, 4, still on the y-axis first, but I can go negative 4, negative 1, negative 4, negative 1, and my slope is still positive 4 because negative 4 divided by negative 1, of course, is positive 4. And our data table shows that because we were able to see change in 8, change in 8, change in 8, a constant first difference there. 8 divided by 2, 8 divided by 2, we have a constant slope. Now let's look at this linear function. So this is a little trickier because it doesn't tell us what x is and it doesn't tell us what y is. So we have to use our knowledge of the real world to figure out what would x be and what would y be. So if I think of a graph, okay, in the real world where this is my x-axis and this is my y-axis, okay, we can't just assume that that's x and that's y. A lot of times it'll be given to us in that form where this first column is x and then this second column is y. But again, we cannot assume that. So here I have to figure out what is my independent variable? What is the thing that's going to keep on going regardless of other things? And so I would think, time. Does time just keep on going? And I'm going to say, okay, what if I put time, and here it's in days. What if I put time on this axis? A beautiful spelling here, okay. So let's think about it. Does height depend on the time, or does the time depend on the height of my plant here? So in this situation, we've got a little seedling that we plant, and we're going to see what is the relationship. And so again, I have to think, does the height of the plant depend on what day it is as it grows? Or does the day depend on the height? And obviously, in the real world, we know that the height is going to be on the y-axis, and it depends on the day. So whatever is the independent variable is the x, and whatever is the dependent that depends on the independent, that is my y. So now that I know that this is x and this is y, I'm ready to find my slope. Okay, so change in y again, the same thing. From here to here, positive 4. From here to here, positive 4. Here to here, positive 4. Here to here, positive 4. So I have a common first difference of positive 4 for each interval. And I can call it a common first difference because these intervals are also common. We're adding 2 days, adding 2 days, adding 2 days. So since this interval is the same here, we can call this change in y a common first difference because I have a constant ratio of change in y over change in x. Every time it's 4 divided by 2, 4 divided by 2, 4 divided by 2. So that rate here, because remember, slope is rate. Having a hard time with my pencil on this one. So my rate is 4, because we have to do the change in y first. 4 divided by 2. Change in y on top, change in x on the bottom. If you don't do that every time, you will get the problem wrong. So our rate is 2 what? Okay, because we need units with our rate. Well, we had y on top, so y was millimeters. So millimeters was the rate or the unit on top divided by what was on the bottom. What did this 2 represent? It represented days. So if I calculate my rate, it should make sense, right? I don't say 2 days per milliliter. I say 2 millimeters per day. I should say day there instead of days. So 2 millimeters per day. And that makes sense. And that is why the change in y goes on top, because it depends on the x. Millimeters depends on the day. And that's why we would put that there on top. And this is how we find the slope or the rate when we are given a data table for a linear function.